I wanted to use integration by parts here with us this afternoon is to look at how to find the antiderivative of certain types of functions we've yet to be able to antidifferentiate. Integration by parts is a nice little kind of tool in our chest to be able to take other antiderivatives for different types of functions. We know that the derivative of the natural log of x is 1 over x, so therefore the antiderivative of 1 over x is the natural log of x. I've yet to describe what the antiderivative of the natural log of x is, though. We can use this antiderivative with integration by parts. Take a wild guess. You got a 50-50 shot at it. What would u be equal to, and what would dv be equal to?
Is u equal to x?
There is no x up here. There's really two pieces. Natural log of x and dx. U is ln x, okay? Luke says, let's try u equals ln x. So then dv would be dx. I would find du by taking the derivative of my u substitution. So u would be whatever the derivative of the natural log of x is, so that it's not going to go with just 1 over x. v would be, okay, well, what do you have to antidifferentiate? What do I have to take the derivative of to get to dx? The derivative of x would be 1 dx, so therefore the antiderivative of dx would be the other x itself. Okay? So that seems to make sense to me. Once again, say you didn't do it right the first time. Say you had u and dv substitution switched around. What if I said that u equals dx and v equals dv equals the natural log of x? Wouldn't finding v just be kind of like answering the question we're already trying to answer in the first place? If I want to know what v is, given that dv equals the natural log of x, if I want to know what function has the derivative of the natural log of x, wouldn't that just be kind of like finding the antiderivative of the natural log of x? What we're already trying to figure out in the first place. So that doesn't make too much sense. Typically, your u function is what's more easily differentiable, and your dv substitution is what's more easily antidifferentiable. It's a lot easier to take the derivative of the natural log of x than it is to take the antiderivative. All right, so let's put this together. U times v. So the natural log of x times x minus the antiderivative of v du. X times 1 over x dx. This first term is pretty much set to go. X times the natural log of x to carry it out. X times 1 over x would just be 1. What's the antiderivative of 1? X. There you go. Using integration by parts, we were able to produce the antiderivative of just a simple natural log function, natural log of x dx. Of course, you could always check your work by differentiation. Since integration by parts comes from using the product rule, I would need to find the derivative of x ln x using the product rule. First times the derivative of the second, plus the second times the derivative of the first. So take the natural log of x times the derivative of x, which is simply just 1. The next term, what is the derivative of x? That's just 1. The derivative of c is nothing, so I don't have to worry about that. X times 1 over x is 1. Bring down to minus 1. Two ones on the left and the right cancel out. And yeah, we're just left with the natural log of x, which is exactly what I started with. So it seems to make sense that our antiderivative is correct. Integration by parts helps us take the antiderivative of the natural log of x. It also helps us take the antiderivative of inverse trig functions. First semester, when we were doing derivatives, I defined the derivative of arc sine x to be 1 over the square root of 1 minus x squared. And therefore, in our last standard, we defined the antiderivative of that. We defined the antiderivative of 1 over root 1 minus x squared to be arc sine of x plus c. We've yet to take the antiderivative of arc sine x, or any inverse trig function for that matter. What do you think u and dv should be?
U is arc sine x.
U is arc sine x, all right? So typically u is whatever is more easily differentiable. Shay says, all right, try u equals arc sine x, and that sounds reasonable. As good a guess as any. Leaving us dv as the same as dx. Take the derivative of u, take the antiderivative of dv to figure out the other two parts. You want to use your formula sheet? The derivative of arc sine x would be 1 over root 1 minus x squared. And what is the antiderivative of dx? Or what is the antiderivative of 1 dx? What has the derivative of 1? Just x itself. All right, let's put some of this together here. The antiderivative of u dv, what I assigned for arc sine x, and dx is equal to u times v. So arc sine x times x minus the antiderivative of v du. X times 1 over root 1 minus x squared would simply just be x over square roots of 1 minus x squared dx. I just multiplied these two together, put the x on top. Slide that over here. Now it's in frame. Sorry about that. Took u times v, x times arc sine x that you're seeing here, minus the antiderivative of v du. Multiply these two together. 1 over root 1 minus x squared times x, written together is x over root 1 minus x squared. See, I see x arc sine x to break down. How do I take the antiderivative of x over the square root of 1 minus x squared? You're thinking arc sine x, which is a good thought. That would mean that, okay, let's try and fit it with some of those substitutions. Luke said maybe arc sine x is a good thought. A squared equals 1, so then a equals 1. U squared equals x squared, so then u equals x. But I just want du on top for that antiderivative as you're looking at your formula sheet. If u equals x, then I have a u on top rather than du. Decent thought, but I think we're going to go about it a different way. What could I set u equal to if not using that sort of process?
You could take the composite function.
Yeah, so let's just call u what then, Chen?
1 minus x squared.
Sounds reasonable to me. One way doesn't work, try something else. Inside that square root is another function, 1 minus x squared, so let's try u substitution with that sort of process. Du, the derivative of 1 minus x squared. 1 has a 0 for the derivative. Minus x squared, that derivative is negative 2x dx. That's how we're going to get the x dx from the other part of my antiderivative there, okay? If du equals negative 2x dx, that means that negative 1/2 du equals x dx. I can replace x dx, the opposite half of du. So let's see what we've got here. Minus negative 1/2 du. So let's just switch the signs, put plus 1/2. I have the square root of u on bottom, or equivalently, that's negative 1/2 du as an exponent. What's the antiderivative of u to the 1/2? What's the antiderivative of u to the negative 1/2?
2x half.
What exponent, though, has to be here? If I bump up the exponent, what's 1 more than negative 1/2?
Positive 1/2.
Do I need any constant out in front? I'm trying to make 1/2 by taking the derivative. Is the derivative of u to the 1/2 1/2 u to the negative 1/2? I think so. I don't believe I need any other extra multiplier or constant to complete this this antiderivative. If I check my differentiation, the derivative of u to the 1/2 is 1/2 u to the negative 1/2. So we're good to go there. Plug in our u substitution to write our final answer in terms of variable x rather than in terms of u. Integration by parts. A nice, slick way to answer derivatives of log functions, as well as derivatives and antiderivatives of these inverse trig functions. This negative 1/2 here is u in the bottom or top? Bottom. So if it's got a square root in the denominator, when I write it in its exponential form, it's a negative 1/2. Does that make sense? And then when I take the antiderivative of that, I actually have to increase the exponent up to 1/2, right? Good. Good. Okay, we've got a little bit of extra practice there on doing integration by parts. A couple of different ways there. Let's try this. Let's make it a little more complicated now with this sort of setup. What is the antiderivative of x squared e to the x dx? What makes this question a little bit different as opposed to some of the practice we did yesterday and earlier this afternoon? got to find the antiderivative of x squared e to the x. I think in class yesterday, we did the antiderivative of x e to the x. What's different about this one? It's x squared. What we're going to actually have to do here is integration by parts twice. I can do integration by parts multiple times to reduce this down to its final answer. Since it's a second degree x squared to start with, when I do integration by parts for the first time, it takes it down to x to the first power. I also need integration by parts again to get my final answer. I can do integration by parts multiple different times. Take a wild guess. If I had x to the third, how many times did you have to do integration by parts to get your final answer? 3 times, right? Once to get it down to a quadratic, one more time to get it down to a linear, then you get your final answer after doing integration by parts for the third time. I wanted to focus today on integration by parts for those log and inverse trig functions, as well as multiple repeated integration by parts procedures like you're seeing here. All right, everything begins with this question. What are u and dv going to be? dv is e to the x dx, you bet. If u is x squared, when I take the derivative of that, it reduces down to a linear term. It doesn't reduce down to a constant, so that's why I'm thinking I probably have to do integration by parts one more time, right? If dv is e to the x dx, what is the antiderivative of that? Which function has a derivative of e to the x dx? Just the e to the x. Those ones are always nice to get because they require a lot of fun. All right, u times v would be x squared e to the x minus the antiderivative of v du e to the x times 2x dx. I do integration by parts for the first time, and it produces this statement here. I need to do integration by parts again when I factor out the 2 to evaluate this antiderivative. I've got x squared e to the x minus 2 times the antiderivative of x e to the x dx. I took it from x squared e to the x dx to now x e to the x dx. Integration by parts, one more time. Not every single antiderivative can be done with one integration by parts. Here's an example where it takes multiple integration by parts, right? Look for that clue out in front. X squared means do IDP twice. X to the third is IDP 3 times. See, u equals x for this integration by parts. dv is another e to the x dx. Again, v is e to the x, and du goes all the way down to dx now. What it needs to do. Be done after the second round of IDP. Gesundheit. Carry down the first term. X squared e to the x minus 2 times what I need to do using integration by parts to evaluate the antiderivative of x e to the x dx. So minus 2 times u and v again, minus the antiderivative of v du e to the x dx. let's see what we got here. X squared e to the x to keep bringing down, minus 2x e to the x. What's the antiderivative of e to the x dx? E to the x. I have minus e to the x, it's an extra negative 2 multiplier out in front, so plus 2 e to the x plus c. Finish that up. Pause there. How are we thinking, everybody online?
I'm all good.
Good.